Hello, everyone, and welcome to the second lecture, Measurements and Significant Figures. Measurements in chemistry are composed of dimensions, capacities, quantities, or the extent of something. So we may want to measure mass, volume, length, time, temperature, pressure, or concentration, and we often measure any or all of these in laboratory experiments. So we will practice doing that during lecture. There are two systems of measurements we're going to look at. One is the English system, which you're probably familiar with, where we measure inches, feet, ounces, pounds, quarts, gallons, miles. The metric system, however, is the system that's used more often in science, where the base measurements are grams, meters, and liters for mass, length, and volume. And you'll begin to see why these are the base measurements, because all of the powers of 10 in the metric system relate back to the base. Meters are the base unit for length, as I just said, and the abbreviation for meters is this lowercase m. You don't have to memorize this definition that I'm giving you. 1 meter equals 1.09 yards in the English system, but I just am giving you that value for a reference. Metric system mass units, again, the base unit is the gram, and it's denoted by this lowercase g. Again, you don't have to memorize this value, but about 28 grams equal 1 ounce in the English system. It just gives you a reference for a gram. Metric unit volume is denoted by the liter. That is the base unit for the metric system, and it's given this uppercase L. And again, while you don't have to memorize this, 1 liter equals 1.06 quarts in the English system, just for a reference. In terms of metric length, metric mass, and metric volume, when you convert to the metric system, we're going to use the same values, the same powers of 10. That makes the system a lot easier because you don't have to memorize all of these different values. For example, in the English system, we could have length that is a yard or a feet or an inch or a mile. With the metric system, we're going to have meters, and then we're going to put a prefix in front of those meters, and we memorize which power of 10 that prefix is related to. So we don't have to convert between hundreds, literally, of different units, because we know what the units are for every type of measurement we're taking. For example, if we're measuring length using the metric system, 1 kilometer is equal to 1,000 meters. 1,000 is equal to 1 times 10 to the 3 in scientific notation, which we'll go over scientific notation soon. If we look at mass, then, so we just looked at length, if we look at mass, 1 kilogram, so we looked at a kilometer up here, and we said that's 1,000 meters. If we look at a kilogram, that's 1,000 grams. If we go to volume and we look at a kiloliter, that's 1,000 liters. So you can see how the metric system, if we just memorize that kilo, the metric prefix, is equal to 1 times 10 to the 3, or 1,000 of our base unit. And again, base unit for length is meters, base unit for mass is grams, base unit for volume is liters. Then we can do conversions for length, mass, or volume by knowing the same conversion factors. Let's look at milli. So milli is 1/1000th. That would be 1 times 10 to the minus 3. So 1 millimeter, again, we're looking at length, is equal to 1/1000th of a meter, or 1 times 10 to the 3 would be the power of 10 that you would memorize associated with milli. If we look at, for example, mass, 1 milligram is equal to 1/1000th of a gram. And if we look at volume, 1 milliliter is equal to 1/1000th of a liter. Also in the metric system, a couple of things that you'll want to memorize. 1 cubic centimeter is equal to 1 cc, a cc being a cubic centimeter. And 1 cubic centimeter is equal to 1 mil. So in the chemistry lab, we use mils more often than we use cubic centimeters, but you will see cubic centimeters used sometimes with density calculations. Deciliter and cubic centimeter are commonly used in a clinical laboratory. And so lowercase d, uppercase L, that corresponds to a deciliter. 1 deciliter equals 100 mils. Again, 1 cubic centimeter is equal to 1 mil. They also use in clinical milliliters as well as microliters. And we'll talk about the power of 10 that's associated with microliters. Remember from the previous slide, for milliliters, that power of 10 is 10 to the minus 3. For microliters, the power of 10 is 10 to the minus 6. So again, you're going to have to memorize these metric system prefixes and powers of 10. So the prefixes are on this side over here, and then the powers of 10 are here. You don't have to memorize that 10 to the 9 is a billion or 10 to the 6 is a million, because you should know that. And if you don't know that, you can quickly determine that on your calculator. What I want you to memorize are the powers of 10 that are associated with each of these prefixes. So the best way to do this is probably flashcards, where on one side of the flashcard you'll write giga, on the other side of the flashcard you'll write 1 times 10 to the 9. Another flashcard, you would write mega on one side, and then 1 times 10 to the 6 on the other side. Because 1 times anything is just equal to that anything, you can leave the 1 times off if you want. But what I want to bring to your attention is that when we look at scientific notation, and we will be very soon, so if we look, for example, at giga, 1 times 10 to the 9, and I just want to point out to you that this 1 is called a coefficient. And then we have our exponential term, which is this 10 raised to some power. So that's our exponential term of scientific notation. And then the 9 is the exponent. And sometimes that exponent is going to be a negative exponent. Sometimes it's going to be a positive exponent. In terms of giga, it's a positive exponent. But if we look at nano down here, you can see we still have an exponent of 9, but it's a negative value. Again, the quickest way to be able to memorize these is to construct flashcards and then work on the flashcards. This is about a 15-minute task to memorize all of these. So let's do a learning check and fill in the blanks that relate to the base units here. You should do this slide, so you should pause on this slide, go back and memorize all of the metric system prefixes and powers of 10, and then come back and do this as a little quiz for yourself to make sure that you've memorized all of them. So kilogram, kilo we looked at, that is 10 to the 3. And since we have kilograms, that would be 10 to the 3 grams here. And then 10 to the minus 12. So what is 10 to the minus 12? And again, we have grams. 10 to the minus 12 is pico. And so that would be picograms. What about nanometers? And so we talked about nano on the previous slide. I pointed it out to you real quick. So that is 10 to the minus 9. And again, because we have meters, that's going to be 10 to the minus 9 meters. 10 to the 6th grams. 10 to the 6 is mega, and because that's grams, we're going to use the symbol for grams, so megagrams. And then centiliters. Centi is 10 to the minus 2, and because our units are liters, that's going to be 10 to the minus 2 liters. And then 10 to the 9 hertz. And I'm going to leave the last one for you to do and move forward. So let's identify the correct conversion factor here. Is it A, B, C, or D? So we have gigameters equals 10 to the 9 meters. Well, we know that giga is 10 to the 9. So would B be correct? 10 to the 9 gigameters equals 1 meter? I don't think so, because giga is 10 to the 9 itself. So that's a really large value. If we had 10 to the 9 of that really large value, we would have a huge number of meters. And then C, 1 gigameter equals 10 to the minus 9 meters, but we know that's not true because we know that 10 to the minus 9 is nano. So it looks like A is correct. Let's talk about significant figures, because whenever you are taking down measurements, you not only need to know about the metric system, because our units are given in measurements. Most often our units of the metric system are the measurements we use. But we also use significant figures. So we need exact numbers and inexact numbers if we're going to write an entire significant figure. The exact numbers, or certain numbers, are numbers that we know because whatever piece of equipment we're reading has calibration marks associated with it, and we're reading those calibration marks. But when we write a significant figure value, it's also going to have an inexact number, or a number that is uncertain. That's going to be the last number we write down, and that's going to be our best estimate by reading between the lines. And we'll talk about what that means with a couple of examples. But that value has some degree of uncertainty associated with it, and so it introduces some uncertainty into our significant figures that we're writing down by convention. What is that uncertainty? It could be associated with accuracy or precision, or it could be associated with limitations on the measurements, either the measuring device or our ability to observe and read the value that's on that measuring device. So what do we mean by accuracy and precision? An accurate measurement is close to the true or the correct value. So for example, a hole in one, that's an accurate play in golf. A precise measurement is close to the average of a series of repeated measurements. When calibrated instruments are used properly, then the greater number of significant figures you have, the greater the degree of precision. Significant figures are what tell us the precision of a particular piece of equipment. So if we have more significant figures, we know that the piece of equipment has a higher level of precision. Let's think about accuracy versus precise. And so, for example, if this is our target, and let's just look at 3 different cases here. So this is our target. Here's our data. In one case, here's our data in another case, and here's our data in yet another case. All right, so remember, accurate means you hit your target, like a hole in one. So which one of these 3 cases would be the most accurate for all of our data? That would be this first case over here. The most accurate for all of our data. All 3 of our data values are very, very close to the target. Have they hit the target? Not exactly, but they're pretty close. We have over here just this one value right here that's pretty accurate, but the other two are not accurate at all. They're kind of all over the place. Which is the most precise? Well, it looks like most precise is between this one, this set of data, and also this set of data. And the reason is because those data values are all in agreement with one another. That's what precision is, when the series of values are all in agreement with one another. But what we know is that in one case, they're accurate and precise. In another case, they're inaccurate but precise. And how could something like that happen is the question. There's a couple of different ways that this can happen. Number one, maybe because all three of those data values are clustered, the calibration on the piece of equipment is not correct. So the equipment needs to be recalibrated. But the other way that that could happen is if you mix your chemicals wrong in the first place, and then you ran the experiment, you're going to get data that's clustered. They're all going to be precise, but none of them is going to meet the target because you didn't mix your chemicals correctly to start with. So that could give us the second option there in the middle. The last one, not precise, not accurate. So what do you suppose is happening there? And I can tell you that usually what's happening there is that the experimenter is just going too fast and they're doing sloppy work. And so their data is just all over the place. Clearly, it's not the piece of equipment. The piece of equipment gave us at least one data value that was pretty accurate. So that means that the equipment is calibrated correctly, and it's probably experimental error that's causing that. Errors arise from a lot of different sources, and we just talked about a few. Error is inherent in the equipment or the procedure that you're using. You can have volume changes due to thermal expansion or contraction, temperature changes in the room. So if we're doing an experiment in the lab and it's particularly hot, that can impact our experiment. If we're doing an experiment in the lab and it's raining outside, that moisture can impact our experiment. We talked about improperly calibrated equipment. If you have improperly calibrated equipment, you're going to get a lot of different groups of students using that equipment, and they're all going to be getting precision data, but it's not going to be accurate. Procedural design allows for variability, or maybe not enough measurements. And one of the things that students hate to do is repeat an experiment. The best way to get the most accurate data, the most reliable data, is to repeat the experiment at least twice and take an average of the two values you get for those two trials. The other issue is mistakes and blunders that you know you've made, and usually in the lab when students make mistakes, they know they've made mistakes. When they've been sloppy, they know they've been sloppy. That data should absolutely not be used. You can have spillage, you can have incomplete procedures, you can be reading the scales incorrectly, you can be using the measuring devices incorrectly, typically because someone's just in a hurry and they don't take the time to do the experiment correctly, and so their data turns out pretty bad. Measurements always have error, even if you're being very, very careful. So you want to record all of your measured numbers, including the first estimated digit. Again, these digits are called significant digits or significant figures. And then you want to conduct one more trial and take an average in order to reduce the error. Then you calculate the percent error. And so how do we calculate a percent error? Usually to calculate a percent error, you're going to take your experimental value. You're going to subtract the theoretical value or the accepted value. The theoretical or accepted value, that's the value that you're going to find in the literature, in a CRC index or in a Merck index or in an Aldrich index, where they give you theoretical values. The other way that you can get a theoretical value is by calculating it. And we're going to divide that by the theoretical value and multiply it by 100. and that's going to give us percent error. Significant figures again introduce this amount of uncertainty, and that's going to become more clear to you as we start looking at taking a couple of measurements. The digits are all recorded that are exact numbers, and those exact numbers come from the calibration marks on the piece of equipment you have, and then again, one uncertain digit or inexact value that is estimated. There are two types of important information that we get. One is the measurement magnitude, which tells us the precision of the equipment, and the other one is the measurement uncertainty, which introduces some uncertainty into the value, but also alludes to the precision of the equipment. Significant figures are the digits in a measurement that are known with certainty plus the one uncertain digit. So all of those together compose the significant figure that you're going to report for a given value. So let's look at how all of this happens with two examples here of graduated cylinders. And so if we look at the very first graduated cylinder over here, we want to know what are the exact numbers or the digits we're going to record with certainty, and what is the inexact number or the digit we're going to record that's going to introduce uncertainty into our overall value. So we look at this graduated cylinder and we say, okay, this is 20, it's labeled, and this calibration mark up here is 30. It's also labeled. But that means that this one must be 21, 22, 23, 24, 25, 26, 27, 28, 29, and then 30. So these calibration marks are changing in the ones place. Because they're changing in the ones place, we have to, because we have calibration marks that are changing in the ones place, we have to estimate in the tenths place, the next place over. So we're looking to see where we at in this region, and we're going to estimate what that value is. So we know that we have 21, and now we're going to estimate the next value over, which is going to be again in the tenths place. And if we put 9 lines between 21 and 22, where do you suppose this line is coming out? So 1, 2, 3, 4, 5, 6, 7, 8, 9, just about. And so that means we're at about 1, 2, 3 maybe, so 0.3. Okay, the 21, this is our exact numbers because those two digits came from a calibration mark. The 3 is our inexact, or our digit that introduces uncertainty into our measurement. But the 3 is important because that tells us the precision of this graduated cylinder is to the tenths place. So we know this graduated cylinder differs from the one to the right of it because the precision differs between those two. And lastly, we want to make sure that we add our units, and in this case, these are both mils. So let's look at the second graduated cylinder to the right, which is more precise. We can tell because it has more calibration marks, and those calibration marks will give us more precision in the data that we get out of this graduated cylinder. So we see here that we have 20, but this is 21 up here. So that's 20, that's 21, and that's 22. That means that we have 1, 2, 3, 4, 5, 6, 7, 8, and 9 calibration marks between 20 and 21. Each one of those are representing the tenths place. So here we have 20.0. This one is 20.1. 20.2, 20.3, and I could keep going, 20.4. But you get the message that we're changing the numbers in the tenths place. If we're changing the numbers in the tenths place, that means we're going to estimate to the hundredths place associated with this particular graduated cylinder. And so it's more precise because the measurements are to the hundredths place, where the measurements in the graduated cylinder to the left were to the tenths place. So let's see if we can figure out what this volume is right here. So we know that it is 21 again, but the question is 21 point what? Well, with calibration marks, we have 21. Here is 21.1, 21.2, 21.3, but it doesn't go to 21.4. So we have 21.3, and now we're going to read between the lines. So if we had nine little lines between these two right here lines, then where would we be at? And it looks like maybe we'd be at about 21.32 mils. And again, now we're looking at these 3 digits being exact, and this 1 digit here being inexact. So we're always going to have only 1 digit that's inexact. And that will be the last digit that we record. Now, before we move on, I just want to say, maybe some of you didn't get 21.3 on the left side graduated cylinder. Maybe you thought it was 21.2, or maybe even 21.4. Maybe on the right side, you didn't get 21.32. Maybe you thought it was 21.33 or 21.31. The fact is that those would all be correct values. Now, if you said something like, on the right-hand graduate cylinder, suppose you said something like 21.42. That's not correct because the volume doesn't go up to 0.4. It goes up to 21. This is 21.00. And then we have 21.10. And then 21.20. So it never goes up to 21.4, so that would not be correct. But if the last digit, the estimated digit, is slightly different, then your value that you record is still going to be correct. Now you notice on the value that the publisher has for the graduated cylinder on the left, they have 21.3 mils. And then the graduated cylinder on the right, 21.32 mils. Again, this inexact digit that's here can vary a little bit. This is the inexact digit for the right side graduated cylinder, and your measurement would still be considered 100% correct. Let's look at the guidelines for significant figures, and the guidelines that catch students up the most are the zero rules. The non-zero digits are pretty straightforward. If we have a number like 593,673, like this one here, we have 1, 2, 3, 4, 5, 6 significant figures, because all non-zero digits are considered to be significant. Zero guidelines. The zeros between non-zero digits are going to be significant, and it doesn't matter if there's 1 0 between 2 non-zero digits or multiple zeros between 2 non-zero digits. All of those zeros between 2 non-zero digits are going to count, and so associated with this number here, we have 1, 2, 3, 4 total significant figures. Leading zeros never count as being significant figures. And so it doesn't matter if you have a decimal or not, leading zeros do not count as being significant figures. They are called placeholders. So here we have 1, 2, and 3 zeros that are leading, and then we have a non-zero digit. So we start counting with that 5, that non-zero digit, and then this 0 is between two non-zero digits, so it also counts as significant. So that's 2, and then the 2 non-zero digits count, so that is a total of 4 significant figures. Trailing zeros are significant only if the number contains a decimal point. So in this case, these trailing zeros count as significant. So we have this one, which is a non-zero digit, then a 0 between two non-zero digits, it counts. The next 1 counts. The 7 counts because it's a non-zero digit. The trailing zeros count because there's a decimal in the number. So we have 1, 2, 3, 4, 5, 6 total significant figures here. Trailing zeros are not significant, and for this class, I know it says generally, there are certain rules that we'll look at with a worksheet where that generally will come into play. But generally, they're not significant unless you're told otherwise, and there are certain types of notation that can tell you otherwise that we're going to look at. So in this case, with this particular value, you have 2 non-zero digits here, the 3 and the 7, and then that's followed up with 3 zeros. So those trailing zeros do not count, and so you have 2 significant figures here. In terms of rounding off, these are the same rules that you learned early in elementary school. If the first digit to be deleted is 4 or less, then you drop it and all of the following digits. If the first digit to be deleted is 5 or greater, then that digit and all that follow are dropped, and the last retained digit is going to be increased by 1. So let's look at a couple of examples. If we want to round 0.4327 to 2 significant figures, and this is what we're being asked, to round it to 2 significant figures. This is the first significant figure here because leading zeros never count, and 3 is the second significant figure that we're going to keep. We examine the next value over, which in this case is 4 or less. It's a 2. That means that we drop that digit and all the digits that follow. So our rounded number to 2 significant figures is 0.43. In the bottom case, again, we want to round to 2 significant figures. So this is our first significant figure, and 5 is our second significant figure. So we're going to evaluate the 7. That value is 5 or greater, which means that we're going to increase the last retained digit, this 5, by 1, and then we're going to drop the 7. That gives us 26 rounded to 2 significant figures. Let's look at a learning check and make a determination about how many sig figs we can predict for each of the following. So we have trailing zeros here. Trailing zeros are never significant unless there's or generally are not significant unless there's a decimal in the number or unless we're told otherwise. And we're not told anything otherwise, and there's no decimal in this number. So that means that 1,000 has only 1 sig fig. 0.00235, and according to our zero rules, leading zeros never count as significant. So those are out, and these are all non-zero digits. So that means we have 3 significant figures here. 10,000. Now here's a case that I was talking to you about where we are told otherwise. So this plus or minus 1,000 means that our precision on this particular significant figure, this value, goes to the thousands place. And the thousands place is here where this 0 is. That means that that 0 is now significant. It has become significant because they told us it is. They said 10,000 plus or minus 1,000. So here we have, instead of having one significant figure, if we didn't have that plus or minus 1,000, we now know that we can trace our significant figures to the thousands place. That gives us 2 significant figures because that 0 now counts. Next number has leading zeros, and we know leading zeros don't count. It has trailing zeros, but we know trailing zeros count if we have a decimal, and we do have a decimal. So that gives us 1, 2, 3, 4, and 5 sig figs. The next one is easy. It's very straightforward. 12. Those are 2 non-zero digits, and so we know we have 2 sig figs there. The last one is in scientific notation, and oftentimes I'll leave the last one for you to figure out on your own. But I'm going to talk about this one because a lot of you may not understand scientific notation and significant figures yet. So we'll go over how to make a determination of what this scientific notation is in standard numerical notation, but we won't do that on this slide yet. What I'm going to tell you is that the only values you put into scientific notation are those that are significant. And we're only going to look at the coefficient. And so if you remember when we were looking at the metric system prefixes and their powers of 10, our coefficient was always 1. But that's not going to be the case all the time when we look at scientific notation. Here we have a coefficient of 1.23. Those are all non-zero digits, and so we have 3 significant figures in that number. And here is a learning check solution, just in case you need to have a look at it later. So how many significant figures do you predict for each of the following? And I'm going to leave this up to you. The only thing that I am going to correct is a typo here. This should say plus or minus. And for some reason, that plus sign didn't get in there correctly. So that is 546,000 equals plus or minus 10. So let me just go over that one since there's a little discrepancy in it. But if we're saying plus or minus 10, we're looking at the tens place. This is the ones place right here. This is the tens place right here. So that means that this 0 that I have an arrow pointing at and also this 0 count as being significant. We're told that when we're given this information right here. So that means that we have 1, 2, 3, 4, 5 significant figures. And I'm just going to write SF right there. And I'm going to leave the rest for you to do later on. And of course, I always give you the solutions, but I want to give you a little preface on solutions. Do not work from the solutions backward. Every student I have who works from the solutions backward ends up with a poor performance in the course because things are going to get much more difficult. And if you train your brain to work from the solution backward, you're never going to be able to work to the solution. That's a problem in chemistry. So let's talk about the rules for combining significant figures. There's a multiplication and division rule, and there's an addition-subtraction rule. You should memorize these rules. I know I haven't said that here, but I'm telling you now, memorize these rules because whenever you come across a calculation, you're going to need to be able to apply these rules. And sometimes we have calculations with order of operations, so you're going to have to apply these rules independently. So for the multiplication division rule, it's very straightforward. Your answer is going to contain the same number of significant figures as your data measurement that has the least number of significant figures. Very straightforward. Addition and subtraction is a little more complicated. Your answer is going to contain the same number of digits to the right of the decimal point, or the same number of decimal values, as the measurement you have with the fewest number of digits to the right of the decimal point, or the fewest number of decimal values. Let's look at a couple of examples, and let's start with the multiplication division rule. So if you have your calculator, then you're going to put into your calculator 3.003 times 0.0029. And when you do that, you're going to get some value out. And let's see what I get when I calculate this. So what I get when I calculate this is 0.0087087. And then I want to look back and apply the rule. And the rule for multiplication division is your answer is going to contain the same number of significant figures as your data value with the least number of significant figures, because our answer cannot be more precise than our least precise data value. If we look over here, we have 1, 2, 3, 4 sig figs, because zeros between non-zero digits count as significant. If we look over here, leading zeros never count. So those 3 leading zeros to the left do not count as significant. And we end up with the 2 and the 9 being the only significant figures. So we have 2 sig figs here. That means that our answer is going to have 2 sig figs, and we're going to have to do some rounding. These leading zeros never count, those zeros to the left in our answer, but the 8 counts and the 7 counts. And since we're going to round to 2 sig figs, we're going to look at the next value and we're going to ask ourselves a question about rounding. Is it 4 or less? Is it 5 or greater? Turns out 0 is 4 or less. And so we just drop all of these numbers, and our answer is actually 0.0087, which has 2 significant figures. Now let's look at the bottom example. And so for the bottom example, we have 7,240 divided by 233. And what I get is 31.07296. I'm sorry that line keeps happening in here. I don't know why that's happening. Let me try to write it over here by pressing too hard. 0.7296133734. That's what I have in my calculator. So I want to make sure that I know how many significant figures I have here. So there's no decimal in 7,240. That means that trailing 0 does not count. So I have 3 sig figs because I have 3 non-zero digits there. And then in 233, they're all non-zero digits. They all count. And so I have 3 sig figs there. Because it's a multiplication division rule, my answer is going to contain the same number of significant figures as my data value with the least number of significant figures, and they're both the same. So I know I'm going to have 3 sig figs. That's going to be this one, and this one. The next one over is the one I'm going to evaluate. Is it 4 or less? Is it 5 or greater? Well, it's 5 or greater because it's 7. That means that I'm going to increase the last retained digit by 1. And everything else is going to go. And so my answer is going to be 31.1. And here's your solution. So let's take a little closer look at the addition subtraction rule. Again, the answer should have the same number of decimal places as the quantity or the data value you have with the fewest number of decimal places, or the fewest number of places to the right of the decimal. That's describing the same thing in 2 different ways. So we look at the first value that we have here. There are 3 decimal places, or 3 values to the right of the decimal 0.247. That gives us 3 places to the right of the decimal. If we look at the second number, the 41.36, we have 2 places to the right of the decimal. And if we look at the last data value, 125.2, that gives us only 1 place to the right of the decimal. That means that our answer cannot be more precise than our least precise data value, which is 125.2, only going to the 10th place. So our answer is going to be rounded to the 10th place, and we'll have only 1 decimal there. So let's do a little bit more complicated question. And this has gotten a little bit jarred here. That's just parentheses, and that's 17.6 minus 13.73, in case you're not seeing that very well on your computer. When we have a problem like this, we go back to order of operations. And because this has subtraction, we have the addition subtraction rule. And because it has multiplication, we have the multiplication division rule. Order of operations says we're going to do this part first. So that means that we need 17.6 minus 13.73. So what I get is 3.87. And now I'm going to apply the addition subtraction rule. And the addition subtraction rule says that your answer will contain the same number of places to the right of the decimal as the data value that has the least number of places to the right of the decimal. Well, 13.73 has 2 places to the right of the decimal. And 17.6 has 1 place to the right of the decimal. So that means our answer will have to have only 1 place to the right of the decimal. But here's the catch. I'm not done with this calculation yet. So I don't round yet. What I do is I underline that 1 place to the right of the decimal so I know I can keep track of where my significant figures are supposed to be. And the next thing I'm going to do is the multiplication step. I know that the 3.07, because I'm applying the multiplication rule now. So in that rule, my answer is going to have the same number of significant figures as my data value with the least number of significant figures. Well, 3.07 has 3 sig figs. But because I have to round to where the 8 is in the 10th position, my other value has 2 sig figs. So my answer is going to have 2 sig figs when I finalize it and round it. So I have 3.87, and I'm going to multiply that by 3.07, and that gives me 11, again, 11.8809. Okay, I'm just scribbling that out because I put a line through it for some reason. So if I want 2 sig figs, that means that I'm looking at this one and this one, and I'm going to evaluate this 8. Is it 4 or less, or is it 5 or greater? Well, 8 is 5 or greater. That means I'm going to increase the last retained digit by 1, and the rest of these are gone. And so my answer is going to be 12. Okay, I normally leave the your turns for you all, but I think that one is a little bit tricky, and I felt like we needed to work through it. So now let's talk about scientific notation. We've been looking so far mostly at standard numerical notation, but there's also scientific notation. And the scientific notation is a system that we use in which a decimal number is expressed as a power of 10 and then raised to some exponent. So what are the rules, the typical rules? The decimal point in the decimal number that we're going to designate when we convert standard numerical notation to scientific notation is usually moved to the position that gives a number that's less than 10. That's not always the case, but generally speaking, if we're going to convert standard numerical notation to scientific notation, that coefficient, we want it to be somewhere between 1 but less than 10. The exponent for the exponential term is going to be equal to the number of places that the decimal point has been moved in order to get that number that is less than 10. If the exponent is positive, that means the original decimal number, the coefficient, was 10 or greater. If the exponent is negative, that means the original coefficient was less than 1. For numbers between 1 and 9, the exponent on the 10 is going to be a 0. So let's look at an example and see if we can convert this standard numerical notation to scientific notation. And we are going to maintain 2 significant figures. The reason we're going to maintain 2 significant figures because we have all these trailing zeros and we know that they're not significant and we don't have any plus or minus some place value to tell us otherwise. So we're assuming that we only have 2 significant figures here, 9 and 3. If you remember, I told you earlier that when you convert standard to scientific notation from standard numerical notation, you're only going to include the significant figures in your coefficient. So that's why we're maintaining 2 sig figs. Now, we have to back an imaginary decimal up. So if you can imagine that we have a decimal in this number here, and we know that we have some imaginary decimal there because this number is indeed 93 million. So we back this decimal 1, 2, 3, 4, 5, 6, 7. So we're just going to put this 7 up here because we know we've moved the decimal 7 places to get a value that is somewhere between 1 and 10, but less than 10. So that gives us 9.3. That 7 is going to be our power, our exponent, on the exponential term 10 to raise to some power. And we look at the 93 mil and we know that that number is greater than 1. So therefore our exponent is going to have a positive charge on it. So 9.3 times 10 to the 7, representing again our significant figures, which are just the 9 and the 3. Now this should give you a good idea about why all those trailing zeros don't count as being significant figures. They're just placeholders. Just like the 10 to the 7 indicates to us that there were 6 zeros there. But we know they're all placeholders. So this is just your solution. Let's try another example here. Now we have a value that's less than 1. When you have an original coefficient that's less than 1, you know your exponent is going to be negative. So let's think about how many places we have to move this decimal. 1, 2, 3, 4, 5, 6. So I know that I moved it 6 places. I'm just going to write that down. And because my original number was less than 1, I know that there's going to be a negative sign in front of that exponent. How many significant figures do I have here? The 3 and the 7 are the only significant figures because leading zeros never count as significant. So I have 3.7, where I moved that decimal, times my exponential term, which is 10 raised to an exponent of 6, and the 6 is negative because my original number was less than 1. And here is the solution for that if you get stuck later on. So let's talk a little bit more about significant figures in scientific notation. Again, I just want to reiterate to you that only the significant figures become part of the coefficient on the scientific notation. So here we have only these 2 significant figures, the 3 and the 7, and those are going to be the only ones that appear in our coefficient of our scientific notation. Over here, for example, we only have a 9 and a 3 as being significant figures, and so the 9 and the 3 are going to be the only digits that appear, in our scientific notation. And I just give you a little tip for when we start calculations. If you're multiplying exponential terms, you add the exponents. And if you're dividing exponential terms, you're going to subtract the exponent in the denominator from the exponent in the numerator. That's the end of our slideshow for significant figures. And so I hope that this helped you understand a lot of different things about how to record significant figures, how to do calculations with significant figures, and also how to use scientific notation.